Hey ladies and gentlemen, welcome back. We're finally in our third class of differential equations. Let me go over a couple of still outstanding logistic items that people asked about. Number one, how do we upload the homework? I got several emails about it. I'm going to post a tutorial from the fall semester, but I also just want to show you. You go to course content over here on the left, and you guys follow my screen? You go into week one. Oh, actually, no, don't go. Week one is a good place to go to, but that's not where I meant to go. Homework one right here. We click on it. And guess what do we do from here? We navigate to browse local files, and I think you know the drill from there. Navigate down to the PDF, put it in. Am I making any sense?
Yep.
All right, I'll take silence as permission to proceed. So guys, first things first. Again, gamma function, little quick summary, rebuke, and now that we had a chance to sleep on it and see what was going on last week, I just wanted to touch quickly back on a gamma function marked by, oh no, gotta increase the font here. So gamma is marked by the capital Greek letter, and it is defined as a integral of a ratio of really two functions. So we have variable t, e to the t living downstairs, some polynomial, and I'm going to purposely mark it as a constant -1 living upstairs, dt. And the limits of integration are kind of fun, but they're here. It's from 0 to infinity. And by the way, this should be not an x, but the constant goes here. Before I hopelessly lose you and lose all of your attention here and resolve, I just want to give you a quick summary and resolution on this. By the way, this is very often represented as, so we have a quotient, right? But it is more frequently represented as an integral of a product. T to the power times e to the negative power. By the way, any ideas on why is it represented as a quotient? Very practical matter from Calc 2. Interactive class, please keep your mics on. Unless you have, like I said, unless you have a very loud dog or army of kids running around, it just helps to keep it on if you want to speak up. So what's easier to integrate, a quotient or a product?
Oh, product by a long ways.
Now I'll help you out. It is a product. So, Ken, you're on mute as always. So, right. Want to give you a quick reminder of what we looked at, and here's how the gamma function really works. So, gamma of 1, we choose the value that we can put into gamma, and then we milk that value in our integral from 0 to infinity. T to the constant was living inside of these parentheses. So we're going to plop 1 instead of the constant. It's going to be 1 minus 1 e to the negative t dt. Am I making any sense on how mechanics of the gamma function evaluation works?
Yep.
It's like fifth time, guys. I ask a question, I don't get any feedback. Yay or nay?
Yes.
Good.
Okay,
Yeah,
is my
makes sense.
speaker off? Sorry, one sec. So, gamma of 1, constant goes right here. Constant goes all the way up in here. And then you can use integration by parts, or you can use Wolfram, and you are basically asked to evaluate an integral from 0 to infinity of e to negative t dt. You can use, as I was saying, Wolfram, or by integration by parts. You can very quickly arrive to the fact that this integral will going to be minus sign here, e to the negative t, evaluated from 0 to infinity. And if you remember your fundamental theorem of calculus, then this thing is evaluated at the upper limit minus this thing evaluated at the lower limit. Am I making any sense there? Have you guys seen this stuff before?
Oh, yes.
Okay. So, and by the way, I guess zooming out would not be a bad idea. But what is we can rewrite this first part as -1 over e to the infinity minus gives you a plus, right? What is e to the 0th power?
Just 1.
1.
1.
And what is 1 divided by e to the infinity?
0.
Oh, so the answer becomes 0. Am I making any sense? All right.
Yeah.
Another quick reminder that in general, gamma of an n, and this is where last week got a little jacked up, gamma of an n could be evaluated by the formula of n minus 1 factorial. Can we get behind this?
Yeah.
Yep.
Yeah.
So then, what is gamma of 1? Gamma of 1, by our formula, is 1 minus 1 factorial. But what is 1 minus 1? It's a 0
Zero.
factorial.
Would be 0.
Right? But it's also that wonderful, wonderful, wonderful integral from negative infinity, excuse me, from 0 to positive infinity, t to the 1 minus 1 divided by e to the t dt, and that whole thing, evaluated to 1. Am I making any sense? This, my dear friends, is the real reason for why 0 factorial is 1. Because what was bugging our mind before is how factorial of n, which is defined as just the product of integer numbers, 1 times 2 times 3, all the way times eventually n, how is a 0 factorial not 0? Well, because of gamma function entering into the picture. And I wanted to show you quick syntax, and I just can't urge you enough, guys, to master Wolfram, because this is part of the big benefit in this class, is the usage of Wolfram. It's free, and it's browser-based, so it's available to you mostly anytime. Okay, let me run the syntax, and you're going to have this in your videos, so no need to write it down. But when you type things in, it really helps to see that it echoes back an important thing to you. Right now, I entered n for general power, right? If I were to change n to 1 and hit enter, Wolfram is going to tell me that, oh, okay, this is effectively gamma of 1, and it outsources a lot of computation to the cloud, and it spews at you that the answer of this outstanding integral is 1. Am I making any sense? Okay.
Yeah. Yeah.
I remember we were looking at that idea of gamma. Actually, let me do this slightly differently. One sec. So then, if we are on that same train, gamma of 2 is the same thing as this number. Let me give you generic formula. Gamma of a constant, and it doesn't have to be beauty of gamma function. That doesn't have to be integer. Gamma of a constant is gonna be constant minus 1 factorial. Can we get behind that formula? Am I making any sense? All right. Write to you 2 things on the little sticky note and put it in the corner, at the lower corner of your screen, to your left or to your desktop, because those are 2 really cool formulas. Gamma is defined as an integral from 0 to infinity, t to the constant minus 1 divided by e to the t dt. This is a really cool fact, and somehow, in its all glory, it works out for integer numbers to be a factorial. Really mind-blowing. So, are there any questions on this part? Let's then see what the gamma of 2 gonna be. Well, the gamma of 2, by this formula, is gonna be this constant, 2 minus 1 factorial, which is also known as 1 factorial. What is 1 times itself? It's basically 1, right? Am I making any sense? Let's not stop there. I just want to drill this into your consciousness because I promise you there will be multiple, there's like a whole zoo of really exotic esoteric functions. There are gamma functions, there are Bessel functions, there are Aries functions. They're all out and about to kick your behind. Similar way they were kicking my behind. But the good news is, they're not that mathematically complicated. If you stare at them long enough, they become your good friends because gamma is really a ratio of a polynomial over the exponential. That's all there is to gamma, truly, at the end of the day. Am I making any sense? All right.
Yep.
All right, let's see. Gamma of 4. Help me out here. Tell me what you write. Using the generic formula, how can I translate this into a factorial?
3.
Well, right. At the end of the day, it's going to be 3, but in the process of sausage making, it's going to be 4 minus 1 equals 3 factorial. Making sense?
Yeah.
All right. So last but not least, for example, gamma of 6 is going to be what?
5. 6 minus
Right.
1.
6 minus 1. You got the gist. All right. Let's go to I pre-canned a couple of computations here. Let's go to Wolfram and let's calculate gamma of 2. And then I promise you we'll move on. No, okay. We'll do a couple more and we'll move on to homework and I'll show you the tip that's going to, in my opinion, help you immensely to do the homework. All right. Look at this. Gamma of 2 is 2 minus 1 is 1 factorial, right? Gamma of 4, all you gotta do is change this number, right? And hit enter. You guys with me on that? Gamma of 4 is 3 factorial, which is 1 times 2 times 3, right? Are you guys shocked with the fact that this is 6? Kind of expected, right? By the way, we don't want to go through the misery and define gamma every time. Wolfram is smart enough where I'm just going to say gamma of 3. Oh no, we said 4, right? Gonna hit enter, and out comes the same exact result. You guys with me on that? Oh, so much easier. Oh, cool, right? Here comes the biggest kicker of them all. This is why I wanted to show you there is so much more to math, and not strictly speaking necessarily buys you super a lot in differential equations. But bear with me, it's a quest of the exploration. You ready? This is going to be amazingly cool. Promise you. All right, check this out. All right, let's see what the heck is a gamma of 10. Oh, come on. Don't do me like that. Where's the 10? Gamma of 10, my friends, is a 9 factorial. Well, that's really, really great. It comes up to be 362,000 with some change, right? Okay, well, that's amazing. Let's see. Are you ready for a mind-blowing thing? What is gamma of 123? Why am I saying that? Because gamma of 123 has, my friends, 203 decimals. Holy moly! What the heck?
Ew.
Oh, and here's my favorite button right here. Where is he? More digits? Oh, dude, show me more digits. I want to see more digits. You want to see more digits? Yeah, there it is. They tell you more. There is a more digit button here that's somehow not showing up for me right now. And the cool question is there a pattern? Are there any numbers that are repeating themselves? I wonder.
Professor, is that a 10 to the 202nd?
Huh?
Is that a 10 to the 202nd?
It is indeed. You want to vomit there, right? Hold your vomit. Let's go 1, 2, 3, 4. Mind blow up. Because my
You can't even say that number.
Oh, sure I can. What do you mean? It's 4.13 times 10 to the 3,277th power. What the hell?
I mean, there's no longer words for that word. It's just
And mind you, show me more digits. Oh, you want to see more digits? There it is. Oh, you want to see even more digits? What the hell?
oh my God.
And then the real question becomes, I wonder if there's a pattern here. If there's anything repeating. Like, look at this column. Oh, there's a 7 right here, 7 right here, 7 right here. Oh, another 7. Maybe there was a pattern to that. Or would you be able to even graph a complexity of how does the number of digits in the exponent growth as you throw in an extra digit into the gamma? See, right now gamma has 4 digits, right? Let's make it 5. Pay no attention to that. And you know what? It is a short number that has 10 to the 45,000 power digits in there. And part of the reason why math is freaking useful is because somebody coded that. It took Wolfram less time than it takes you to sneeze to do this computation. How about that? Am I making any sense? Are you guys crying there? I was like, why did I say up for this?
Yeah, the fact we're all muted. We're all crying.
All right. Okay, guys. Any questions on any of this? Does this look like a magic to you? Because it probably should. But I also should tell you that if you approach this and you get over your initial shock, you're like, how the hell did they do this? I'll be honest with you, they probably don't compute it all at once. There's probably a file somewhere on the server that hosts these numbers in the table, and it just looks up your entry up against the answer, and it just spits out an answer for you, and you're like all sorts of amazed here, right? But supercomputers computed all that stuff, tabulated it probably, and stored it in the cloud. All good stuff. All excellent reasons for studying mathematics. All right, so before we move on, one of the super redeeming features of Gamma was, yeah, that's right, we don't have to calculate just integer factorials, because as I was stressing to you before, can you see my screen here okay? We can figure out Gamma of, this is going to be bizarre, of 2.5. So Gamma of 2.5, follow the nose here. Just obey the formula. What is a Gamma of 2.5 in terms of a factorial notation? Just humor me here. It's 2.5 minus 1 factorial, which is 1.5 factorial. What the hell does even that mean? What the hell does that even mean, right? Well, I don't know. Let's ask Wolfram. Gamma of 1. Okay, not 1.5. Of, what did I say? 2.5. And it has an answer. It is 1.329 with some change. So gamma function allows you to extend the notion of a factorial to non-integer positive numbers, to non-zero real numbers. Am I making any sense?
So do you have a way of graphing that?
We do. I'm glad you asked. I'm truly glad you asked. Just type in gamma, and it's going to show you things you want to know. Okay, not the letter gamma. Come on. If you're curious, it's in the appendix 1. You're going to see a graph of this function, but here it is. Okay, here is the bloody function of gamma. It looks like a hyperbola here, and it's a graph that goes to points of a factorial, but then so much more, because you can see that this is a continuous graph. You with me so far? Yay, nay, maybe?
Yes.
Yes. Any questions on that?
Many, but it seems like that's just gonna further complicate things. Is that like it almost looks like a tangent function.
It does,
graph.
but except it's not. So, but
Right.
there's something else that's extremely important here, and we're going to move on pretty soon. But I just wanted to stress your attention on something very cool. Guys, can you still see my screen?
Yes.
Can you? How would you recommend I would plot this equation for my students? What would you recommend I use? It starts with a D. What really nifty-looking, clean, online webpage can I use to plot this? What do you think?
Desmos.
Good. Outstanding. Desmos is a tremendously useful utility up until the end of calculus. Because by the end of calculus, Desmos becomes pretty helpless. Desmos cannot plot a gamma function. You know why? Because here we have an explicit formula that you can type in into the graphing calculator. Gamma is a family of functions that is defined by evaluating gamma of n. That is defined every point on this graph, every single point that you can stick your pencil into on this graph came from plugging in the x value for n right here, and then doing the computation of this sort. Am I making any sense? It is not a function that has a closed form solution. Every point on this graph is determined by taking the x-axis, by taking the x-coordinate and evaluating this monstrosity for every step of the way. Desmos is going to puke, because Desmos is not a computational utility. Desmos is a graphing thing. Am I making any sense? Pretty cool, huh? I bet you woke up this morning, you didn't think much of anything about this. And as I was saying earlier, and this is where I had a pretty nasty typo in the last video, we could evaluate classic example, gamma of a half. Using our factorial definition, that's 1/2 minus 1. Yep. That's really, at the end of the day, comes up to be like mind-blowing thing. A factorial of -1/2. How do you even start to approach that? Well, my dear friends, it's a very simple, relatively speaking, very simple integral to calculate. And you would have you would have t to the power 1/2 divided by e to the t dt. You can do integration by parts here. I would recommend sending denominator this as a u, and then you can massage it out. But you can also use internet, go to Wolfram, and type in, oh, that's right, gamma of a half. By the way, guys, real quick, where's my graph? Half is roughly speaking over here, right? On the scale. Let's click on this.
Roughly.
So gamma, excuse me, roughly speaking right here, if this is the x coordinate and I have my plot, I can sort of trace up and see the y coordinates of that point, and it's going to be clearly greater than 1, but also obviously less than 2. Am I making sense thus far?
Yes.
Yes? Okay, let's ask Wolfram to do this quick computation for us. I mean, you can define this in terms of improper integral, and I recommend doing it first number of times so you can get used to that. But gamma of a half becomes the square root of pi z. Am I making any sense? So in other words, this is really mind-blowing. Really, really, really mind-blowing. If this is correct, then a factorial of a negative fraction somehow becomes the square root of pi. I have no other gesture to show that. Am I making any sense? All right, guys, questions on that?
Can you pull up the graph of the gamma function one more time?
Hello.
So how is 0 equal to 1? According to this graph, it should be a...
No, and that's exactly the point. I don't have a... Alex, you're asking two different questions. I say that gamma of 1 is 1 minus 1 by definition is a 0 factorial. That thing equals to 1. Gamma of 1. When x equals 1,
I gotcha.
Gamma is 1. Are you guys with me on that? When x is 1 over here somewhere, y is also 1. You with me on that? By the way, attained by really painful, laborious computation. If I would plug in 0 into gamma, right? First of all, can you guys see the y-coordinate of gamma when x is 0? It doesn't exist because it's asymptotically. It's a vertical asymptote. It has a discontinuity there, right? The thing plummets to the negative infinity and approaches positive infinity on the right. So these two limits diverge. And if you actually go and plug in 0 for the gamma as an input, x equals to 0, then you're effectively asking to figure out what is -1 factorial, and that is a big frowny face because it doesn't exist. Am I making any sense?
Okay.
Just to prove the point.
I see where I made my goof.
Don't worry, we'll make goofs, right? And here Wolfram says, what are you even asking about, boy? It's a plus or minus infinity. It doesn't make sense. You with me on that? All right. By the way, it's not going to make sense because there are logarithms when you integrate by parts, and those guys really puke and gag when they get negative numbers put into them as an input, at least for the sake of this course. That's part of the reason why these guys are discontinuous. They have asymptotes at the negative numbers. So, but, okay. All of that is tremendous. Moving on. Homework. I want to give you a tip that I shared with somebody today. It's not something that I learned, but it's something that I want to teach you. All right. Where are we? By the way, here's my favorite quote from Morpheus. Did you guys see that? That's right. There's good old Morpheus dazzling Neo there with his quotes. All right, so.
Beautiful.
Isn't it? So, Wolfram, again, I want you guys to fight with tools. I'm showing you this not because I want to drill in home syntax of Wolfram. Monkey can learn that. But I want you to use the Wolfram and other mathematical resources intelligently. Here's what I mean by that. Guys, if I were to, pardon me for insulting your intelligence, but if I would type something like this, right, I can certainly use Wolfram for evaluating this. You guys with me on that? Many of you ask, why are we in differential equations and you're showing me how to do 1 plus 2? Right?
Where's the second shoe?
A second shoe is flying down from Mars. That's going to hit us in a moment. So, with me so far? We can even go as far as ask Wolfram to solve this super complicated equation. 1 plus 2 equals x. It's good. Aye, sir. Got it. 1 plus 2 equals x. X equals to 3. Duh. Right? But it solved a really primitive equation for us. You guys with me so far?
Yeah.
Here's the
We're following
shoe.
you.
Here's the shoe flying like an asteroid from the from Mars. Where is our? Okay, so let's for a moment assume you were presented with this outstanding homework set, and you are asked for bonus question to do what I'm about to show you, and I really want you to do it. That's why I'm giving you 25% bonus. It might even make it 30% bonus. So watch this thing. Number 14 is not asked of you, but let's just do it anyway because we can using Wolfram. You can do it by hand if you want, if you have another 25 minutes to spare. I don't, and I don't like to make mistakes in front of students and embarrass myself even more than I have to. So here's the drill. It asks you to verify that this formula for y, I don't know if you can see my screen all right, a little grainy, but can you resolve this?
Yeah.
Here is a really monstrous looking formula for y. It's a product of negative product of cosine and a ln, which in turn has a secant and a tangent sum plugged into it as an argument. There, right? Ooh, not looking good at all. You, my friends, are invited to check that if you take a second derivative of that guy, add to it this expression on top, you're gonna get tangent. You guys with me and you have eyes on the prize on what are we asked to do? With me on that? Now there are two ways. There's a really miserable way, and that's like 17, 18, and 19, and probably early 20th century to suffer through this. And I invite you to go through this. I invite you to do number 11 and 13 by hand so that you appreciate the beauty of this. But let me offer you an alternative approach instead. So, all right. I have this a little bit pre-canned to save us a little bit of time. I have this expression for y typed up in the notepad right here. And step number 1, don't get sassy. Do this step for me, please. If you decide to go this way, don't be like earlier me. Do this step. First step, type in your expression for y into Wolfram. Let it echo it back to you. And make sure you got this right. By the way, Wolfram is a little peculiar. It treats natural logarithms as log. But if we can brush that out under the carpet for a moment, this looks pretty similar. Negative cosine, ln of secant plus tangent. You guys with me on that?
Yes.
All right.
Yes.
This is really y. Okay? Watch this. I am pretty good at copying and pasting, right? I think most of you are pretty adept with that too. So look, how do I ask Wolfram to take a second derivative of this expression?
A little apostrophe at the end.
What is
Slap
it?
a D in front of it and then put two
You
apostrophes.
can no D's. Either Leibniz notation or Newton notation. So if it's D, then dx squared at the end. All right.
Right. So that would be your
That would be
y.
very involved. Look, you can do this. Oh, actually, D caret 2 over dx squared. And that might or might not work because that's a lot of syntax. Let me offer you one better. Just encapsulate this in a parenthesis and put the double prime after it. Am I making sense? If you were curious to calculate second derivative of this function, which we, by the way, assume that the function is differentiable and continuous and defined, right? Those are all wonderful terms from Calc 1 and 2. Assuming it is, then Wolfram is going to be able to pull this lifting. Oh, look at that. Yeah, it echo-etched it that the second derivative, it knows. It detected the variable. The second derivative of this expression with respect to x is this lengthy blah, 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 blah. You with me on that so far? But look, for the sake of argument, what I'm deleting right now, and if I would somehow had a way of typing in, okay, what's showing in this prompt bar is really y double prime. You with me on that? So the structure of the equation, not Morpheus, the structure of this, where did it go? Okay. The structure of this left-hand side says, if you somehow have a y, take its second derivative and then add y to that thing. See what's going to happen. Okay, I think I can do that. Can you guys see what I'm trying to do?
Yeah.
Instead of, y doesn't mean anything to Wolfram, but if I would paste that guy in there, come on, right? And then plus parenthesis that thing again. My control V doesn't work here, so, right? And I'm going to hit enter. I effectively just entered the left-hand side of this problem. You guys with me on that?
Yes.
Second derivative plus y. Wolfram is going to do computation for me on the left. Ready to see the result? I am. Look, after all this mumbo jumbo, it says that the result of the left-hand side is
Tangent x.
it's tangent, right? And the equation also says, oh, well, if y was a solution, then this y should satisfy this equation, namely, make this equality true. Does it?
Yes.
My request to you, in order for you guys to get the bonus, is to attempt number 11, number 13, and then I think 2 more, of course by hand, but also using Wolfram. And here, if you're going to manage to type in this equation into Wolfram first, right, and let it echo back to you, make sure you didn't screw up, didn't fat finger something else, right? Good. Then basically try to recreate the structure on the left and see if second derivative of this mumbo jumbo minus 6 times the first derivative of this mumbo jumbo plus 13 times this expression again, what is this going to produce? And if it produces 0, which Wolfram has no idea in advance what it should produce, so we're going to do through it and do the computations. You're outsourcing the heavy lifting to the cloud. Are you guys with me so far? Am I boring you to death?
I really appreciate this explanation, Professor, because I was checking those type of problems, and maybe it's because of my language, but I was having a hard time what the question was asking for. So really, I have an understanding now what's going on this. And thank you.
Well, you're welcome. I'm glad. Again, I'm not a piece of toast.
I had that same
you don't have to butter me, but
No. I was just sweating.
But does it make sense?
Beating on the bush. Yep, it makes sense.
Why am
Bergen,
I
you weren't the
showing
only one who didn't get it.
Why am I showing you this? Because A, I want you to practice and understand what's being asked of you. And secondarily, we have until Thursday to submit the thing by midnight, so you have plenty of time to do this. And
What if we already submitted?
The what?
Can we resubmit?
You can resubmit. I'll leave the resubmission problem. No problem. But please don't email it to me. Please be good doobies and go through the motion and upload it through the Blackboard.
I didn't. So I tried to upload the first homework and I forgot a page. And it didn't have an option for me to.
Yeah, I think. Yeah, resubmit. Sorry to cut you short. I think there is a stipulation, and I'm going to lift that. I think by default, Blackboard defaults to one-time submission, but I can easily waive that. So we're going to take care of that. All right. Any questions? You guys feel comfortable using Wolfram and doing by hand for any of these problems, realistically, as an approach. If you enter it half decently, then basically it doesn't become that hard. I want you guys, again, Alex, Summer, Hannah. Hannah, did you know that your name is a palindrome, by the way? it reads the same way from left to right as right to left. It's a fun math word, palindrome. So, guys, I want you to, Flowbots, back in 2011, there was this really popular band called Flowbots, and they had a very popular song. You might have heard it's called No Handlebars, but I listened to their whole album. They're really cool. And they have a song called Fight with Tools. I want you to be able to do problems and fight with tools. I don't want, like, mere typing in, syntax, because that's pointless. I want you to think outside of the box a little bit and use the tools that are just a click away from you. They're free and they're super potent. Use them. Am I making any sense? Fight with tools. Okay, do I have permission to proceed, or are there any questions?
So, for that extra homework, Professor, do you want proof of us showing then we use the Wolfram or
yeah, I want to get the thing, please slap together print screens of this, right? You typed in your y value, you hit enter, right? And then you enter them as derivatives. You hit enter. What matters to me for number 11, take a print screen of this work, right? Number 13, guess what? Same requirement. Those 4 problems, I remember the numbers, but those 4 eligible problems, do the motions for every single one. Please understand, I'm doing this for you. The main benefit is in it for you. You stand to gain. I stand to give the credit. There's nothing in it for me, right? But if you do this, you're going to drill in home the skill of typing things and working with Wolfram, and you're going to get extra 30% or whatever on your first homework. I think it's a fair shake, right? What do you have to lose? So you've been just voluntold. Yes, it's optional, but it's kind of on the mandatory side. All right? Any questions, guys? You're not going to get penalized if you don't submit it, but it's in your interest to go through the motions. You'll probably be happy you did. And, it might just feel kind of a little bit empowering too. All right. Questions on this? Going once? Mr. Dmitry? Miss Elizabeth? Any questions? Come on, guys. I'm not that good. There's got to be, like, some things that, don't make sense here and there.
Not gonna lie, I just had an aha moment, actually.
Good. Hang on.
I was reading all these problems wrong. Oh my gosh.
And I think the aha then it becomes, hopefully it's like, oh, that's actually a lot more manageable than I thought. You remember that guy that told you, don't you even think about withdrawing if you get overwhelmed? Talk to me. I guarantee you we can help set you back on track, even if you fall a little bit behind. But remember my spiel about spectator sport? It's not enough to watch me do this. Your fingers must touch the keyboard and you must type stuff in. Otherwise, it doesn't work for you. Make sense? All right. Whew, that was my pre-canned little spiel there. All right, moving on to bigger and better. We're going to depart from section 1 and go to section 1.11 to go 1.12. I want to make a distinction between, again, setting up terms, general solution versus particular solution. So, and we're going to pick up a couple of terms that are kind of cool and important along the way. And by the way, those of you who had me earlier, remember that I do lecture notes, but my lecture notes for this class, they're a little bit discombobulated. They're okay, but they are not worth sharing because in part we work with code and we work with math utilities, so I can't write them down. I can't do Wolfram demo for you on the paper, right? So still, if you think you have really good notes, don't be shy to share them with your classmates. Because if you write notes, you put it through your cranium better. Am I making any sense? All right? All right, so general solution meets partial solution. We're going to go into initial value problem with this in a little bit, but guys, you all probably know the solution of this problem. If you are given the fact, you're given an equation y prime equals x squared, can you help me find y from here? Not a particularly difficult one, isn't it?
Yes.
What you got?
X cubed over 3.
I'm listening.
plus C.
Oh,
C.
please don't you neglect that C. You're going to see why in a moment. Super important. All right? Making sense? This, my friends, is a general solution because this represents a whole family of curves. This is a cousin of a cubic function, and depending on this vertical offset C, you can have one of multiple outcomes. You can have this stuff, this stuff, this stuff. Am I making any sense? Do you know which one of these curves is the solution? I'll tell you what, I don't, right? We just found a general solution. However, if we would somehow figure out the value of C and make it equal, or somehow find that C equals to 2, then we have y equals x cubed over 3 plus 2. This guy, and you're welcome to double check me, this guy also satisfies this ordinary first order differential equation, right? If you would take derivative of this y, you're going to get this thing highlighted in the blue. You with me on that? Part of the homework. Why is this considered a first order differential equation? Not a trick question.
Because it's y prime.
Bingo. Did everybody get that? Are there any ambiguities there? Crystal clear or clear as mud?
It makes sense. First order because it's first.
What do you think are the odds of seeing a simple, naive question like that on next quiz 2 on Thursday?
100%.
Not out to get you. Yes, but odds are pretty great. And so please remember that. If you would see more than, first order, right, this would become magically what? Third order, right? You with me on that?
Yes.
Okay.
Yeah.
So let me zoom out a little bit and put a little bit of additional information here. Generally speaking, we're not that lucky to get a family of general solutions. Generally speaking, from our experimental data, if you work in the field or you do measurements, you're going to get a bunch of like little dots. Okay, they all mean to look like hyperbolic functions, like the x cubes right over 3. The dotted representation of the graphs before we connect the dots, it's called translating from Ukrainian.
Is it like contours?
Direction field. Basically, the little dotties or little dashed lines that would indicate a trajectory of something, how the particle would move. If you would place a particle right here, that particle will move along this potential field. Am I making any sense? Right? It's not going to want to go along this trajectory or any other trajectory. You with me on that? So the initial condition of initial placement of the particle turns this problem into an initial value problem, and this gives rise to something that we're going to discuss in a moment. So again, where you place the particle is your initial condition. It's going to be very important in a moment. But before the part, very useful and very frequently used 2 pieces of mathematical jargon here. Direction fields are dashed representation of the general solutions. You with me on that? And the graph of a solution, this graph of a solution, it also has a unique name. It's called I'm going to find a place to write, an integral curve. Am I making any sense? Anybody cares to guess why is it called an integral curve? The reason is pretty obvious. What operation did we perform to go from, this was not meant to be here. What operation did we effectively perform from going from having a derivative to not having a derivative?
We integrated it.
Right? Thus, this graph of a general solution is called an integral curve. You with me on that? Book goes over many interesting things, but I think that I'm a pretty wordy guy. When you look at the book's explanations are just massive. They talk for 2 pages about very, in my opinion, not much. It's a nice way of saying little. So they tell you that a function is a solution to an equation if it basically makes this equation sign true. If you have derivatives on one side and functions and other business on the other side, when you plug in function for y and it satisfies the equation, then it's true. Right? Did I confuse you guys more than, was it more harm than good, or did you sort of follow what I was thinking?
Followed.
Okay. And if you don't tell me, then I have no way of knowing. Ms. Summer, you good with this?
Mm-hmm.
Dave, are you on board? I know Mr. Rice.
I'm on board.
Outstanding.
Yes.
All right. So, wanted to show you by the means of example, introduction to an initial value problem. And we're going to use, it's a very popular acronym. We're going to be using, we'll borrow a book from, we'll borrow a page from physics book. Suppose we were given y double prime, and y double prime looks like a constant, 9.8 meters per second squared. Okay. Do you guys recognize this number at all?
Acceleration from gravity?
Yeah, that's acceleration metric function. Thank you very much. Acceleration due to gravity on Earth. Making sense?
Mm-hmm.
Makes sense.
All right. I would love, my goal is to find a general solution that satisfies the second order differential equation. Okay, tell you what. We don't know any better right now. I'm going to omit units for a moment, and I'm going to zoom in. And if I want to undo differentiation, which tool do I have in my toolbox?
Integrate it.
Integration.
Greater.
Like that?
Yeah, you did it twice now.
Yeah. All right, word of caution. There will be a dx here and a dx here. Word of caution. At the end of the day, we'll have to integrate twice because we have 2 derivatives, right? It's a second derivative, rather. Not 2 derivatives, but second order derivative. You would man that?
Yeah.
This thing is not integrating twice. It's not the same as, watch this. Do you guys feel me, and do you feel the qualitative difference here?
What is the 2 S's?
So this is a term from multivariable, and this is not a prerequisite for this class. But by the way, this is a double integral or integral over an area. If it went over your head, that's fine, because it's not a prerequisite for this class. But for those of you who had a pleasure of living through Calc 2, I'm sure Heather would appreciate it, and I know who else had Calc 2. Come on, guys, speak up.
Yeah, I Calc 2.
Yeah, me too.
Did multivariable.
I think you would fully
Calc 2 was a
appreciate the
prereq.
subtlety of what am I stressing on. Am I making any sense? This is not the same as that. This means integrate twice.
The right one means integrate twice, Professor?
Nope, the left, oh yeah, I'm sorry, the right one, right. This thing here means integrate me twice. Integrate the thing inside of parentheses and then take that result and integrate it again with respect to dx. This means something totally different. This means integrate twice but with respect to 2 different variables. This is the way it's written right now, it's rubbish. You're going to have more than dx here. But I don't want to dwell on that too much because not a prereq for this class. If you understand what I'm talking about, great. If you don't, well then just remember that the right way to go to do the integration would be to just do this part. Am I making sense?
Yes.
All right. Well, again, I think the best way to understand the formula and whether or not it's true, it's to kind of do one or two and see what we can do. All right, first integration. Well, I'll do the hard part. I'll do the thing on the left. First integration kills this first derivative thing. So we're going to have y prime as a result of the left-hand side differentiation. What's going to happen on the right? You're integrating
9.8x plus c.
9.8x plus c. Where did c come from?
Is that general constant?
Because there are no limits of integration. This is an undefined integral. Am I making any sense?
Yeah.
Okay.
Should that be a C subscript 1?
Excellent question. I think we're going to have to make it subscript 1 because what are we going to... I don't care to find y prime. I care to have y, right? What are we going to do again?
Integrate that bad boy.
Integrate that bad boy with respect to x's, right? Okay, that's an easy part on the left. On the right, I'm going to do this, right? And this. Do you guys follow and do you see what just transpired?
Yeah.
Okay. Again, I'm doing all the hard work here. You do the easy part. Integral of y prime is going to become y. Whew, that was hard. Now, I did what I promised. You do the rest. What's the integral of 9.8x with respect to x?
So 9.8 will come in front.
Uh-huh.
It will be x squared over 3.
Over
2.
Oh, I'm sorry, over 2.
It's okay, got it. That's the first one. Check. Is everybody on board with that?
Yes.
Yeah.
There's
Plus.
one subtlety we're going to come back to, but let's just carry on, even if you're not 100% comfortable with this. All right. Is that it? Or is there more to it?
Plus bx plus c.
Plus, the integral of
plus c
constant
X.
is cx, right? We picked up
C.
an extra variable. Plus what?
C.
C2.
Am I making sense? All right, technically speaking, guys, and this is where I wanted to remind you, subtlety that you probably didn't pick up or didn't comment. Anything you want to tell me about this integral and this integral here? May I use a yellow color to, let's see. Yeah. Look, guys, this guy is going to be the integral of this thing is going to be 9.8x squared over 2 plus its own c. C, I'll call it sub a. Am I making any sense? Theoretically speaking, it's a random constant there. And then this wonderfulness will also going to have cx plus its own constant of integration. Am I making sense?
Yeah.
And by the way, guys, if you can't see the color, I'm legit colorblind. I'm not kidding. There are some shades that I don't resolve. So if you don't see yellow, please yell at me. I'm gonna change the color. Am I making any sense? All right. This is x, not a subscript. And we're adding these two things. 9.8x squared over 2, here it is, right? Cx, here it is. And this C2 is really a composite thing. It doesn't really truly matter, but it is comprised kind of under the covers of two other components. Am I making any sense? No big deal, just a pure subtlety as of right now. Are we good with that?
Yes.
There's part of the reason why damn pesky constants matter. Because if you integrate more than once, that constant picks up a variable and it's going to be left with you for the rest of your life there, right? It's gonna matter. It's not just the vertical offset anymore. With me on that? Okay. Any questions on any of this? Mr. Sam, Ms. Lee, Ms. Ken, Mr. Zachariah?
If there were limits, we could find the values of C1 and C2, correct?
Right. But excellent question. But typically speaking, in the context of differential equations, we don't have limits because when we don't do integration, okay, that's not a full story. It is much easier to measure a location of a particle at the time 0. You know where the particle is when you start the watch, and then you let it go and it does its own thing. But it's very easy to come with a ruler and measure where it is and measure particles' velocity at a certain time. So I'm not directly answering your question, but I think I'm indirectly am, and I'm segueing us to a bigger part here. So this, my friends, is a general solution. Am I making any sense? Have you seen the stuff from physics before?
Yeah.
Okay, well, maybe not everybody had calc-based physics. I would find it hard to believe that not everybody had calc-based physics by now, but okay, maybe not everybody did. Gee, I wonder, by the way, which way gravitational acceleration typically points? Up or down?
Towards the center of the largest mass.
Okay, in our case, it's Earth, right? In my case,
So
it's my
down?
belly, but in our larger case, it's our Earth, right? So we just let things go, and they fall down, right? So typically speaking, this number is negative. You with me on that? And if we do integration, okay, we kind of left out a negative sign, and that at the end of the day, it's going to precipitate and show up right here. You with me on that? If we were to plot this general solution, okay, I'm losing a little bit of a square there, but we're going to come back to that. If we were to plot this, we're going to have a parabolic curve that, those of you who had me for college algebra, got to remember, which way would the parabola be pointing, up or down? Which way the cup is pointing, up or down?
Down.
Why? You knew this was coming.
Because it's negative.
Negative.
Excellent. So this is upside down. This is a cup that points like this, right? And this is 100% in line with a trajectory of any projectile or any object that's being thrown from the ground up, right? It's going to have a horizontal component and a vertical component. But at the end of the day, it's going to, remember my demo in class, when I throw a pen or like a stress ball to a student and ask people to watch the trajectory from the side. It goes like, wee, boom, like that, right? Making sense?
Yeah.
But this is a general solution. And suppose now we want to know a particular solution. And the particular solution is going to come from
My microphone's being quiet.
from initial value problem. We're going to know, we'll have to figure out the value of these constants, C1 and C2. And in order for us to do that, we're going to be given value of y at some point. Let's just say it's 2. And the value of y prime at some point. Let's just say it's 3. Am I making any sense?
Yes.
Yeah, makes sense.
Then almost there. Then we, there's a lot of chicken scratch here. We had an expression for y prime. Okay, let me go back one step. Expression for y prime was, let's just consider our negative sign here, negative 9.8 x plus c1, right? And then we have an expression for y right here. So in order for us to find them constants, this is probably pretty old news, and you might have seen this stuff before, but maybe not everybody did. And I by the syllabus, I'm obligated to go over this stuff with you. So to find value of C1, use this initial condition. Namely, it tells you that the value of y prime when x is 0 is going to equal to 3. So 3, right, that's the y prime of the left-hand side, is going to be negative 9.8. Plug in the value of x. Over here, right, plus C1. Am I making any sense? In this case, value of C1 is very trivial, right? C1 is just good old-fashioned 3. You with me on that? All right, well, that was pretty nifty. Now, to the value of C2. But in order for me to figure out C2, I need to set the left-hand side equal to something and I need to have an x coordinate to work with. Well, here's my x coordinate. Here's the thing that I'm going to set the left-hand side equal to. And the left-hand side is going to become 2. Then the equation tells you negative 9.8 over 2 times the value of x squared, but x is 0, right? Stop me if you have questions. I'm not into losing people. Plus the value of C1 times x. Well, C1 we calculated. Value of x happens to be 0. Because we're working with this point right here. Am I making any sense? Plus the value of C2. Now let's figure this out. This term drops out because it multiplies by 0. This term drops out because it multiplies by 0, right? And what are we left with? We're left with the fact that 2 is the value of C2. Am I making any sense?
Yes.
Now, let's wrap it up. And let's get a particular solution. We juggle all these things just to get the fact that y, very specific y, that satisfies this exact problem is going to be given to you by, it's a member of general family of functions, right, that looks like this. It has a negative sign right here, plus the value of C1 times x. C1 is 3, so you have 3x. You guys with me so far? Okay, then you tell me what
Yes.
the initial is.
Yes.
Plus what?
That's true.
2 plus 2 plus 3.
That's 2.
This is a specific problem. I mean, this is a specific solution to our specific problem. Am I making any sense?
Yes.
You guys feel like you are somewhat a hair more comfortable with initial value problem. I wanted to generalize it for you and just leave you with this for the closing thought. In general, let me see, am I zoomed in low enough? Nope. Nope. In general, guys, if I have a third order differential equation, something like this, I'm not asking you to solve it. I'm asking you to please help me entertain one question. How many constants will you pick up by integrating this stuff? Okay, let's pretend that y doesn't even live here, right?
3.
Right? Murugan is saying 3. You with me on that? Okay, suppose this wasn't the third order. Suppose this was an nth order. How many constants would you pick up?
N.
N, right? So if you have an nth order problem, you'll need n initial conditions, or n points. In order for you to find a specific solution. Am I making any sense? Because otherwise you'll be stuck with a bunch of those C's, C1, C2, Cn dangling around, right? Am I making any sense? In this specific case, we'll have to integrate n times, so y will equal to x to the n over n. That will be a factorial hanging there. But bottom line, there would be bunch of c's, c1 plus x c2 plus x squared over 2 c3, etc., 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 all the way to the left, to the nth term. Am I making any sense? All right, did I bore you to death?
Don't they have some kind of physical meaning? So like in our original
It
example
will.
we had...
okay, let me see something. Excellent question. It has a geometric meaning, and it's best illustrated. One moment. It's best illustrated using second-order differential equation, because. All right, let me pick up at this. We're almost out of time, but let me pick up at this next time. Depending, hang on one sec. Depending on how far I can, if I can get to this or not. If you have your book in front of you, I urge you to go to page number 14, and let me see if I can bring up a PDF and show you the image. But it basically, okay, while it's loading, let me give you the gist. Second order, how many initial values you'll need? You'll need at least 2 data points. And here's what I'm saying. Before in algebra, we were trying to figure out an equation of the line that passes through a point. But you know what? Honestly, I'll be honest with you. This equation passes through that point. This equation passes through that point, right? There's infinitely many equations that pass through that point. You with me on that?
Mm-hmm.
So if you want to know just the equation, you'll need one value and the slope. But if you want to know the equation and the specific slope, then you're more constrained. Because when you're solving a second-order differential equation, you are answering, come on, show me this. They have a beautiful picture on page 14. Let me navigate ourselves to that. They are saying that, look, at the end of the day, we are interested in, this is the picture I was going for. See, there are many graphs that live in this interval. One of them happens to even pass through the black point of our interest. You guys with me so far? But we can further restrain the problem to say, I don't care to know just the family of curves that pass through this black point. I want to know the equation of that curve that passes through that point and has this pink slope at that point. Am I making any sense?
Yeah, so far so good.
In case of second derivative, you can say that I want to know equation of the graph that passes through that point, has this kind of a slope, and has a certain concavity. Yeah, that's the term, right? You probably heard that before. And that's defined by your second derivative. Is it concave up or concave down? Is it convex or concave? Am I making any sense? Okay, guys, probably not world's best explanation, but but if you revisit example 1, and I purposely don't use examples from the textbook because you can read the textbook without me. You're not paying for the class for me to go over example from the textbook. Am I making any sense? But this example is actually, after all, pretty kind of beautiful. They're talking about the first order value problem, and the answer is going to be dramatically different depending on your initial value conditions. If they're saying that x equals to 0 and y equals to 3, it's going to give rise to this black curve as an answer. If they're going to change the 2 values that you're given and go to the point 1 and -2, never mind the slope, then the graph of your solution will going to be given by this pink curve. We're going to visit how to find them analytically in a bit. We're still at the very early stage of the class. We're giving you a gut feeling for what are we after and not how to get there yet. Am I making any sense?
Yes.
My speaker is on, so you guys being pretty awfully quiet, so I'm not sure what to make of that. All right? All right, I think that's all I wanted to talk about more, but there's always the next class. So this is all we got for tonight. Quiz next time on the homework problems that were posted last week. You will see a monthly survey because I do mean to give you a couple of options on when can we do office hours, and I know different time slots work differently for other people. All right. Do you feel like you guys got something useful out of today?
Yeah.
Let me stop sharing.
100%.
Yes.
Oh, wow. All right. So good. Stick around. I can't tell you everything all in one sitting because I do want you to come back. Right? It's not a one-day seminar. It's a 15-week course for a reason. And I also want to remind you guys, my words will echo and resonate hopefully through time. This is an introductory course. There's so much more that we can do and will do, but you have to just master this first and then come back for more advanced classes. Probably in a different school too. But I'll teach you the basics and then let the smart people teach you more complicated stuff. Am I making any sense?
No, that whole smart people comment didn't make any sense.
All right. Well, think about it.
Oh, I thought you were the smart people. That's why you're getting paid the big bucks.
Yeah, that's right. Well, sometimes. But no, I'm just kidding. Not the smartest kid on the block by any means. But I've been through this rodeo once or twice, and years of experience make me more of a subject matter expert on this. That's why I feel like I have something to share with you. Okay? Any questions?
Professor, probably we're running out of time, I understand.
Yeah, that's right. I remember I promised to show you the other one. All right, guys, you want to stick around for 2 more minutes or maybe 5 more minutes, and we're going to address the question that Mirgan asked earlier about that pesky system of equations. Promise you, it's extremely straightforward. Let me just revisit and think through with you. Okay, so if you have to log off, but the video we're gonna carry on, and you're gonna see it on the blackboard when you need to come back, right? Because I know some people have a 7 p.m. class. All right, so with permission, I'm gonna steal 10 more minutes of your time, and my wife is gonna allow me for it. So, all right, so where was it? Okay, if you can see my screen. Again, did I read your intention right? You were going to ask about that system?
See you, we don't see your screen.
Oh, not yet? Okay.
I'm
bad.
sorry, Professor, I didn't hear you.
No, what I was saying is that, Mirgan, were you going to ask about that system of equations problem right here, number 37?
Correct, yeah, but number 37, it's for homework, so we can explain 38.
All right, yeah, absolutely. 38 is a little bit more involved. I was feeling kinder and more compassionate. That's why I chose 37, but let's work with 38 real quick. And it's actually not that difficult. Actually, why won't we? You're welcome to go through the motions by hand. And, okay, you tell me which way you want me to do it. I can do it by hand. It's going to just take us 20 minutes to do this. Or I can show you.
No, yeah, we can.
I can show you Wolfram implementation of this. And then you can see it for yourself by hand. Okay. So if we go to, need a little bit of hand here. The whole idea, we're given x. So if we were to take a second derivative of this right-hand side with respect to t, do we know how to take a second derivative of cosine of 2t?
Yeah.
That's a chain rule twice, right? Do we know how to take a second derivative of sine 2t? That's a chain rule twice as well, right? Do we know how to take a second derivative of 1/5 e to the t? That's not even chain rule. That's just straight, textbook picture perfect example of exponentials. So you take a second derivative. It's going to be, I think, 1/25 because it is kind of product rule, but in disguise. So the thinking would be to type this in, and guys, I'll need somebody's help because I'm going to switch from the screen. So if you have this open, tell you what, hit print screen real quick, or use a snap tool to capture my screen right now.
That's all right.
Got it?
Yeah, I have my book open on that.
Outstanding. That will work. Let's do it the old analog way. So, all right. What is the left-hand side asking us to do? Take a second derivative of a function, right?
Yes.
What is the function that we're trying to differentiate? Could you please read it for me?
So The first one, Professor?
Yeah.
It's 4y plus et.
Oh, no, I'm talking about number 38. Okay, I have my book too. Hang on. You follow what I'm saying?
Professor, you're talking about cosine 2t plus sine 2t?
Yes, exactly.
Okay, plus
Cosine of 2t
plus 1 over 5 e to the t power.
sine of 2t plus 0.2. Let's go for 0.2. Let's go for what it is. E to the what is it? T, right?
T.
All right.
Correct.
Always a great idea. Don't be sassy. If you think you entered the formula that you want to work with, don't be shy to hit the enter because it's going to help you flush out any kind of mistakes. Is this what we meant to enter?
No,
Yeah.
it's asking for the second derivative.
Right. But what I'm saying is, if we garbage in, garbage out, right?
Yep.
Let's make sure that it echoes to us that this is the formula we intend to work with, right?
Correct. Yes.
All right then. Doom, doom. No, not that. Not semicolon. Boom. Here's our left-hand side, right? By the way, another huge advantage of using Wolfram is you guys will become so much better equipped for, look at this sexy presentation of a formula, if that could be even called that. Look, this is report ready for your calc classes, for your physics classes, for your EMI classes, electromagnetism classes, for any classes. We need to do this work. You just ask Wolfram to do the derivative. It gives you the answer. You do the snip. You picture, you capture that, put in your report. You submit it to your instructor. You get your instructor is going to be all sorts of impressed. Your manager is going to be all sorts of impressed, right? This is very digitized and very user-friendly and ready to be used to submit it to somebody. Publish your results, submit it to your superiors, submit it to your commanding officer, whatever you want to submit it to. Am I making any sense?
Yes.
You don't have to agree with me. Just actually it helps if you disagree, but but all right. And then the right-hand side, if we did everything correctly, right? By the way, I just captured the result of the right-hand side. The right-hand side, excuse me, the second derivative is this. Right?
Correct.
This is our left-hand side. Okay, you know the value for y. The value, excuse me, not the value. The equation for y is given to you right here, right? All you have to do to check if the right-hand side equals the second derivative we just found is to type it in. Or I can urge you to do one better. Remember, work smart, not hard. Fight with tools. What I'm trying to get across here is the following. This upper equation could be rewritten slightly, can't it? Here's what I'm having in mind. Let me paste this into Paint. All right. So these two equations are the same things as, you ready for this? You're going to see a shocking revelation. You ready? Shoot. This becomes a minus. I'm going to subtract these two terms, move them to the left-hand side. And if I do that, then this whole thing is going to equal to 0. Am I making any sense?
Okay.
You with me on that?
Yep.
How should I modify the bottom to attain the same spirited outcome as I have on the top?
Do exactly the same thing.
So tell me,
Negative
this will become
plus
negative. This will become what?
Positive.
Equals to what?
0.
All right, and I'll tell you something else. Wolfram doesn't necessarily know any of this part, right? It doesn't know what it's going to be equaling to. You with me on that?
Mm-hmm.
But you can go to Wolfram, type in this equation, we'll call it equation 1, right? Check out if that equals to 0. Then type in equation 2, the same way you know how to handle your second derivatives, right?
Yep.
And check out if that equals to 0. Well, let me do exactly what I just preached. Second derivative minus 4y minus e to the t. Oh, second derivative of this guy is given to me minus, well, geez, I have to type in the expression for y. That's going to be a little annoying, but nothing we can't handle. Straight from the textbook. Negative cosine of 2t, right? Am I staying honest? Minus sine of 2t, right?
Yep.
Oh, look at that. Minus point, I'm going to call it a decimal, 0.2 e to the power of t. Oh, that was a handful, wasn't it? But I promise you it's going to take you an order of magnitude, if not 2 orders of magnitude longer, with more errors to do this by hand, which 37 shouldn't, but 38 is more cumbersome. Am I making any sense? Than to do it by Wolfram. So the structure here is second derivative of x with respect to t minus some formula, this is known as y, minus e to the t.
Doesn't that y need to be multiplied by 4?
Oh yeah, excellent point, thank you. Well, we will find out pretty quickly. Like that, right? Hit enter. This is a complete another letter soup. I absolutely agree with you here, right? Do you guys see my screen?
Yeah.
Does it echo back in spirit what we wanted to have accomplished on the left-hand side? Second derivative minus 4 times mumbo jumbo, aka y, right? Minus e to the t. You with me on that?
Yeah. So the result is 0.
Ta-da! How nice. But don't stop here, because system of equations is only satisfied when both equations are happy and equal. So, but the good news is we just need to like kind of just juggle around the terms, and we can just modify a little bit sines and cosines, and we're gonna get our bottom equation in no time. Am I making any sense? Because what's inside here, this, guys, do you see stuff highlighted in blue? This is my y. So if I want to proceed to the second equation, I need to take a second derivative of the stuff that I have highlighted in blue. Well, guess what? I'm going to copy it. I'm going to delete this junk. I'm going to clean it up and set it up kind of like I want to take a second derivative of y on the left. Control V, and oh, here's my expression for y already plopped in to the operator of second derivative. Am I making any sense? Am I getting too carried away? Am I losing you guys?
So for the second formula, which is the d square y.
Yep. D square,
dt.
right?
So you're comparing that with the y as we speak right now, Professor,
basically, right? I'm plugging in y into that second derivative operator on the left. Am I you guys with me on that? Then I'll have to subtract 4. Okay, guys, just for the sake of setting up, it's not going to mean anything. It's not going to mean anything to Wolfram, but in theory, I wanted to do this. You guys with me on that? Except x right now means a hell of a lot of nothing to Wolfram. Well, fortunately, I have an expression for x in terms of t. So all I really need to do is to replace this guy, right, with cosine of what, 2t plus sine of 2t plus 0.2 e to the power of t. What the heck happened here? Yeah, sorry about that. Oh, my numlock got it. Sorry guys, my numlock was num plus sine of 2t Did I enter this correctly?
Is that supposed to be second derivative?
Yep, it's hard to tell here, but there are 2 ticks on the left.
Okay.
I don't know, let's hit enter and find out.
Don't you need to add e to the t this time?
Right, that's right. And look, what is our result of the rubbish that I just typed in?
So it's not 0.
It's not 0. It's either really truly not 0 or I screwed up, right? Well, we can check if I screwed up. Let's revisit the syntax, and somebody justly pointed out I have to add e to the t, and is that right? Doesn't look like adding it would make it better. Oh, look at that! Just one sign, put it all back together, right? The problem with these problems is, especially when you do it by hand, one slip of the pen, any of us make one mistake, the whole problem goes into like the tailspin mode. Like we don't just get a little bit wrong, we get severely wrong. We get like out the window jumping wrong, like completely wrong. Am I making sense? I tell you what, and this is why I valued instructors that allowed me to even use TI-89 on exams. I would much rather spend the time to set up the problem and then enter the problem into calculator and hit enter and let it do the math for me, all the mindless just juggling. Yes, you need to understand how to do it, but no, you don't have to suffer through this every time. Am I making any sense?
Yes.
This is why I'm showing you Wolfram. If you're gonna make Wolfram, there's nothing special about Wolfram per se. It just happens to be available online for free in large measure. But if you're gonna make it a part of your professional psyche, you're just gonna be better off. It's part of college here. We're trying to answer the question who you should become, not who you want to become or probably will become, but who you should become. You should become better engineer, best scientist you possibly can, because then you can get a job for EB or Pfizer, and then you can help make next COVID vaccines, which we're going to study, not COVID, but the pandemic spread later in this class. Am I making any sense? And this, in part, answers to why am I here. I'm not that smart to figure out the COVID vaccine, but I can help educate you guys a little bit better and share stuff with you so that collectively we can beat difficult problems down. Am I making sense?
Yep.
All right. Mirgan, did I sort of answer your question?
Yes.
Okay.
Yes, Professor.
And this is part of the reason why I hesitate to post my lecture notes online and to even give a preliminary schedule, because we typically don't go by the schedule. But what matters to me, it's the thorough description of the stuff that we're talking about, as opposed to just me reading to you existence and uniqueness theorem, and it goes like meow, and I'm like, everybody's with me, and everybody's like, oh yeah, and nobody got anything, and we're all moving on, and this is one total merry screw up. Who wants that? Not me. Am I making any sense?
Yep.
You guys feel a little compelled to come back on Thursday? Do I yell at you too much?
You couldn't get rid of me if you wanted to.
I guess you'll find out on Thursday, right?
Well, I always have an option of not logging in, so. Of course, Thursday is going to be award-winning attendance. You know why? Because we got a quiz. And 10 of those quizzes are 30% the grade. And the quizzes
How did the quizzes?
Go ahead.
I was wondering about that. How did the quizzes work? I had accommodations last semester, so I didn't know if you needed me to get an updated letter or not.
No, but so generic answer to how will the quizzes work? Well, it's going to become available at a certain time. I think the time I'll set in the Blackboard, it's 6:15, and then you have until. What do you guys think? If it's going to be 1 or 2 question quiz, and we're going to know better after we take second quiz, but my vision is to give you guys about 10 or 15 minutes to work on the quiz, and then another 10 minutes to sift through the IT, to convert it to PDF and upload it to Blackboard. Can we live with that?
Yeah, that seems reasonable.
Again, I want to think that I'm a reasonable guy, so I'm not out to get you. And I would not do something to you that I would not want to, happen to me. And I would not ask questions of you that are like, dirty or sneaky or like, haha, gotcha. No, that's not me. I'm not one of those type of professors who just, asks you really ungodly difficult questions on the exams. Like, well, I wanted to stick it to them, and I want to see if they can figure it out. Yeah, no, not me. All right. So, Heather, the thinking is quiz is making appearance on Blackboard at 6:15 p.m. on Thursday, Eastern Standard Time, and and its submission window is open until 6:45. Am I making any sense?
Okay.
Let's make it 10 minutes before 7. You have your webcams on for the first 15 minutes while you work on it. Then I don't want to see you battle the IT problems. But I think by now, correct me if I'm wrong, everybody's an expert on how to get a picture of the sheet of paper in front of you into a PDF and upload it to Blackboard. Am I right in my assumption?
Yeah.
All right, let's dissect it. Can everybody manage and has enough technology, it's not a trivial assumption, to take a picture of what they have in front of them and make that into a PDF?
Uh-huh.
Yeah.
That's step numero uno. And step number 2 is to get that bad boy to the Blackboard. Do you guys feel well equipped to manage the second part?
Uh-huh.
Yeah.
Okay, then we're covered. Am I making any sense?
Yeah.
Okay. By the way, a standing invitation. If you know anybody who could benefit from taking this class or seeing this material, who's not going to throw me under the bus too hard, because technically you need to pay tuition to get the credit. But nobody said that you can't sit in, right? Am I making any sense? You're just not going to get a credit, but if you feel like there are some people that can benefit from seeing this, feel free to invite them over. I'm totally open to that. Okay. All right, guys. This is getting late at night, and I'm feeling a little spent out. And we're only 30 minutes past our normal closing time. So I'm going to wrap up with this. If you guys have any questions, please stick around. I'll have a few more minutes to entertain your questions. Otherwise, I'm going to stop the video here. And then I'm looking forward to see you guys back in 2 days. All right?
Thank you. Have a good one.
Thank you, guys.
Thank you.
Thank you.
See you. Stay safe and healthy.
See you Thursday.
Will do.
Okay.
Bye.
Bye.
All right, the video is off. If anybody needs me, I'm here. Otherwise, I would not object to having dinner.